Good evening, Dr. W. This is Nazanet Margia. Today, I'm gonna show you Unit 3 video, Chapter 7 to 9. First, I read the questions. Answer the following questions using videos and post your response to the appropriate folder in D2L. Assignment. Be sure to read each question carefully so you answer all parts. SOP are a class of amphipathic compounds that are incredibly important in our daily lives. Define the term amphipathic, then draw an example of a SOP molecule using a skeletal structure. Next, explain how the molecular structure of SOP allows it to wash away dirt and grease. Be sure you discuss polarity and intermolecular forces in your explanation. My answers is first I define for amphipathic. Amphipathic is a molecular having both hydrophobic non-polar and hydrophilic polar regions. SOPs a form of fatty acids. SOPs have two parts of molecules. Non-polar hydrophobic hydrocarbon, its tail, polar hydrophobic hydrophilic head. Hydrophobic is water heating, hydrophilic water loving. Hydrophobic dissolve in oil or greases, hydrophobic dissolve in water. The chemical representation of SOP is RCOO, sodium, or RCOO, potassium. A chemical formula of C17H35COO, sodium. I'm gonna show you the structure of the skeletal structure of in SOP. We have 17 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 carbon. And then I have in 35 hydrogens, 3 hydrogens in here. All they have in 2 hydrogens. And then the rest of the head area, this area, it's hydrophobic end in the head of the head area, COO, sodium. So in the structure, I'm gonna show you in the around the structure area, in the end of the hydrophobic end, they dissolve in oil and greases. The attraction toward non-polar molecules in this side, all tails, the attraction towards non-polar molecules, heads, the attraction towards polar end, such as water. Hydrophobic end area around in here, it's head. The end is head. The end is head, hydrophilic area. The hydrophobic area, it's tail. It's in this area, head. Hydrophobic end, its tail. I'm gonna turn to chapter number 2. Concentration is the amount of solute per amount of solution. Because concentration is used in a wide variety of applications, there are also a wide variety of units for concentration. Answer the following questions about concentration. Show your work and explain your calculations for each. A. What is the molarity of a solution containing 0.95 moles of sodium chloride in 2.4 liters of solution? In molarity, we're going to calculate I write down my questions too. In molarity equals mole over liters. We have in moles in 0.95 in moles, and then 2.4 liters of solutions. So in all the time we found it in molarity, the mole over liters. So in my mole is 0.95 divided by 2.4 liters. I'm gonna get 0.3958333333. So I use an equivalent, so 0.4 mole per liter. I'm gonna turn B in number B. We got question number 2. It's B. How many grams of dextrose must be added to prepare 215 ml of a 3.0% MV dextrose solution? I found it in dextrose M over V. It's M over V. We're gonna get, I have in 215 milli times 3%, 3.0% divided by 100. So I got in 7.5 grams. C, if a solution contains 2.0 mmol mole over liter of magnesium 2 plus iron, what is the concentration of the solution in milli equivalent per liter? So I using for my calculation 2 point my mole have 2.0 mmol 2 liters of magnesium 2 plus times I have in magnesium 2 plus, and then times 2 milli equivalent magnesium 2 plus. So I cancel out 1 mole of magnesium 2 plus, 2 mmol of magnesium plus, and then 2 times 2 equals 4 milli equivalent grams per liter. I'm gonna turn to number 3. Answer the following using the Bronsted-Lowry definition of acid and bases. Write the chemical equation for the acid-base reaction between acetic acid, CH3COOH, and water. First of all, I use them to equivalent my questions. Write a chemical equation for the acid-base reaction between acetic acid, CH3COOH, and water. CH3COOH and H2 acetic acid it's a weak acid, so I just equivalent for both sides. CH3COOH aqua plus H2O liquid equivalent to the to I transfer to H3O aqua plus CH3COO aqua. So CH3COOH is an acid, H2O is in a base. I turn to B. In your chemical equation, label all the reactant and product using the following term: acid, base, conjugate acid, and conjugate base. My equivalent question, my my acetic acids already I make him equivalent. So CH3COH is aqua, and then it's acid, plus H2O, it's base, in water it's base, and then H3O plus aqua, the conjugate acids, plus CH3COO lose one aqua, the conjugate base. It's give to one in water, in here it is a conjunctive basis. Number C, write the equilibrium constant expression K equals, we don't know. For this reaction, the expression of K equals, it's a constant K equals product over reactant. The brackets mean molar concentration of a molarity. The equation states that. So therefore, the equilibrium constant K equals molar concentration of product over that of the reactant. So the equation for ask us, write the equilibrium constant expression K equals, we don't know the numbers, and then for this reaction, I got in H3O plus, and then CH3COO, its molar concentration of product is H3O plus CH3COO minus over the reactant H2O, and then in the bracket CH3COOH. D, if acetic acid is a weak acid, is the value for K greater than 1, less than 1, or equal 1. Explain how you know. The value of K is less than 1. K is less than 1. Okay. If acetic acid is a weak acid, is the value for K greater than 1, less than 1, or equal 1. Explain how you know. The value of K is less than 1 because a value of K for acetic acid is 1.8 times 10 to the power of negative 5, much less than 1. This indicates there is much more acetic acid in solution at equilibrium than acetate and hydronium ions. F. E. In the human body, pH varies drastically among different organs. How would a molecule of acetic acid pKa equals 4.76 behave differently in the stomach pH equals 2 compared to the small intestine pH equals 8? In other words, which form of acetic acid, the acid or the conjugate base, would predominate in each organ? Explain how you know. If, for example, how molecule of acetic acid pK equals 4.76 behave differently, the stomach pH equals 2. Small intestine we have in pH in 8. If solution pH equal pKa, then equal count of acid plus conjugate base. If solution pH less than pKa, the more acids. If solution pH greater than pKa, then more conjugate base. So stomach, we have in stomach pH value equals 2. So pH is less than pKa. So it is more acids. Small intestines pH value is 8. pH greater than pKa. pH is pH we have in small intestine pH 8 greater than pKa 4.76. It is the conjugate base. Therefore, the solution of both stomach and small intestine, stomach more acids and small intestines, the pH is the solution more than conjugate base is favored. Thank you for giving this chance. This is Netzanet Marga. Sorry about that for some words again and again. My voice is not good for. Thank you for your patience. Thank you.